compromising this a little bit and actually smoothing. So by that, what I mean here is we might want to set this particular row to 45 degrees. We may want to set this particular row here at 5,500 RPM to 35 degrees. Now, we might on paper be giving away a small amount of power and torque, but the advantage here is if the cam timer can track target more accurately, we're probably going to end up with a more drivable car out of it, and really that's more important often than a small paper increase on the dyno alone. All right, with our basic table set up now, let's get back up and running. We'll perform a ramp run on the dyno and see, first of all, how close to our theoretical optimum we've got, and also how well we're tracking those targets. All right, so we can see that we've got our first composite run on the dyno now, and we can see overlaying with the previous reference line in purple, which was 50 degrees. Gave away a little bit in the bottom end, but that's probably more to do with run-to-run variation due to heat soak. Again, really important when we're doing something so sensitive like this to make sure that our engine operating parameters are held as close to the same as we can from one run to the next. This means our engine coolant temperature as well as our intake air temperature, particularly with a turbocharged car. When we are doing multiple back-to-back runs, this tends to build more heat into the turbo and exhaust manifold, which can result in a slight increase in our boost pressure, or particularly our boost response at low RPM. So that's essentially what we're seeing there, but we can see that we've got pretty good control of our fueling here. Our boost pressure is doing pretty much what we'd expect. Let's save that run now, and we'll overlay this with our other runs. All right, so our run we've just done is actually pretty hard to see. It's in red here, and we can see for the most part it's pretty much skirting across most of the tips of all of our other runs. Again, a little bit of variation here, run to run, but that is to be expected. So what we're going to do now is go through the process of optimizing what we've got on the screen right now, seeing if we can get any improvement, any gains. And this is probably the point you're going to come into if you have already got a developed map. So there's two techniques that I'm going to use here. The first of these is we're going to come back into our timing map here, and let's look at what we saw on our graph or our logger from our last run. We can see our cam timing for bank 1 and bank 2 as I scroll through this, and we can see these sort of steps which obviously are doing exactly what we've got on the cam timing map. But what I'm going to do to start with is just smooth these a little bit. I'm just going to change these breakpoints, which of course, if you followed the process through, this should be done a little bit earlier in our process anyway, but we can always change these as we see fit. And often this is important when we do start making changes to our cam timing during these ramp runs. So what we've done now is we've just made those breakpoint changes, and you can see that the ECU has made some small changes here to interpolate those results. Not too worried about those changes there, but what we're going to do is make some of our own here. I'm just going to go ahead and basically interpolate these so that I'm going to smooth off that shape. It's going to, again, as I've mentioned, make it a little bit easier for our cam timing to actually track these changes, and smooth is generally what we're trying to achieve with this sort of change. So that's our first change there, just doing some smoothing, but we want to make sure, of course, that we haven't gone backwards with that change. I've just made some general smoothing, but that might actually mean that I've smoothed the wrong areas. So just want to make another ramp run here and just make sure that we're still at least on track with our last one. So let's go ahead and do that. All right, so we've got our run complete there with our smoothing done, and essentially we saw no real change there. We're at least within the ballpark of a run-to-run variation, and that's going to lead us into our next step, which is what I refer to as bracketing our results. So we've got some numbers in that cam timing map that are pretty close, but we also did take reasonably broad steps there, 10-degree increments for those 6 initial runs we did. So regardless whether I've developed the map in the way that you've just gone through, or I'm starting from a map that I've previously developed, maybe we've made some hardware changes on the car and we just want to see if the cam timing is still dialed in accurately, what we're going to do is make some block changes. So we're going to get our reference run up on the dyno screen, which obviously now we have. We're going to start by making a 10-degree change. It doesn't really matter whether we advance or retard the cam by 10 degrees. We just want to make a change and see the effect of that change. So let's start by removing 10 degrees from the entire table here. So we've done that now, and let's get another run underway and assess the effect of that change. All right, so watching what was happening during that ramp run there, we could see that from around about 5,000 RPM and above, we actually picked up a little bit of power. Didn't see a significant change in the bottom, maybe a slight loss. So let's just have a better look at those 2 runs overlaid on top of each other. So this makes things look a little bit clearer, and we can see, as I mentioned, from about 4,800 RPM actually and above, there's a clear advantage retarding the cam timing 10 degrees there. We can see that we have lost a little bit through this mid-range. And again, we do need to be mindful of making sure that this isn't a turbo heat related issue. So a couple of back-to-back runs just to make sure we are seeing that repeated before I actually made a change would be the course of action that I take here. And likewise, we can actually see that our minus 10 degrees has given us a bit of an advantage right down at the start of that run up to about 3,000 RPM. So let's apply what we've learned there. So up to 3,000 RPM, we want to leave our cam timing as we've just left it. So from 3,500 up to about 5,000 RPM, we want to advance that cam timing back to where we had it. So we'll highlight that area there. Now, we need to be mindful of this, because if I just add 10 degrees here, we're going to see, again, we're getting into the situation where we're making some pretty ugly steps in this table, which is probably not going to give us the exact result we want. So again, it's a case of making these changes smoothly. And again, we can build this up. So what I'll do is I'll start by just interpolating the results here between 4,500 and 5,500 RPM. In the ECU Master software, we can do this using the interpolate vertical function. It gives us a slightly smoother result here. And likewise, we will want to do something similar down here. It's probably actually not so bad here, 3,000 RPM. What I might do is just increase the values there just to give us a slightly smoother shape in that table. So we're just watching while we're doing this, making sure that we haven't got any really ugly changes in this table. So again, we're at the moment trying to follow the exact peak values we're seeing on the dyno. This becomes an iterative process, but let's get another run underway and see how we're looking. All right, we've got our next run complete there. So what I'm going to do is save this, and we'll overlay these with our other composite runs and see how we're tracking with our results. All right, we've got 3 of our composite runs being displayed on the dyno screen. Our yellow run called Composite 2 there. This was essentially developed from those 6 individual runs, building up our cam target table. We've then got our green run here, which is where we have removed 10 degrees, and then our Composite 3 table, which is what we've just done, our Composite 3 run, our last run we've completed there, which is where we've basically taken the wins that we saw from retarding the cam timing 10 degrees and then done some smoothing. So we can see for the most part our white run here, if we get rid of our yellow run, our white run here essentially has given us almost the best of all of the results. We've got a small deficit through this mid-range here from around about 4,800 RPM through to about 5,500 RPM, we are showing a little bit of a decrease. We've seen an increase through this 4,000 to 4,500 RPM region, and we can actually see we've also dropped off right at the top end. Now this is where we need to be a little bit mindful of interpreting our results though, because particularly for those last two runs, I made no changes to the cam timing at high RPM at 7,000 RPM, so we rightly wouldn't expect to see that. So that's a clear indication that we've probably got some run-to-run variation creeping in here, most likely to do with rising intake air temperatures. Given our Subaru STI, it is quite difficult to maintain very consistent intake air temperatures with the top mount intercooler. But the process we're looking through here is essentially a rinse and repeat of this. We're just going to make bracketing changes like this. Now that first change we made there by removing 10 degrees or retarding the timing by 10 degrees, that actually in our instance gave us some pretty significant gains. Often that won't show any improvement, so of course if that's the case, we're going to go the other way. We'd advance the timing by 10 degrees. So we're bracketing each side of the initial composite map that we've developed and just seeing where we've got some iterative improvements or maybe some losses, applying what we've learned to our composite table, our timing table, and then repeating the run. So in this way, it is an iterative process of building up our optimal cam timing table. Now of course, once we've got that cam timing table pretty close to optimal, this is the time to then go back and reassess our fuel delivery and reassess our ignition timing, optimizing those. You may find that there are small improvements available, particularly with our ignition timing. And once you've optimized the ignition timing, it is worth going through another iteration of our bracketing. Probably this time we should be very close to the ballpark, so advancing or retarding 5 degrees instead of 10 degrees is worth just seeing if there is any small improvement. But again, just to reiterate the importance of our getting our run-to-run conditions as close to ideal or consistent as we can. We are potentially looking at quite small improvements from our cam timing, particularly when we're getting down to making 5-degree changes. So of course it's worthwhile making sure that all of our other variables are held as consistent as possible. Our air temperature, our engine coolant temperature, our air-fuel ratio, our ignition timing, and of course our boost pressure. As we're going through this process, it is also worth checking consistently to make sure that your cam timing is actually tracking the targets that you're programming in. So let's quickly have a look at that last ramp run from our tuning software, and we can see here we are on our VVT tab, and we can see our intake cam 1 and our intake cam 2, both following those targets really nicely, so nothing to be worried about here. But this is an area where quite often we can fall into a trap if we aren't actually tracking the targets as accurately as we think. All right, so that's the process we're going through here. Let's head back over to our VVT target table. And we do need to just address the fact that we've got some pretty ugly areas in this table. First of all, we can see here down at 1300 RPM to 750 RPM, we've got this massive step. So we're not going to be tracking or asking for a cam advance at very low RPM because of our low oil pressure. So generally 1300 RPM, we're getting into a region where we might be able to get some reasonable cam control. What I'm going to do is just increase this particular breakpoint here to 1500 RPM. And what we're going to do, instead of tracking a target of 40 degrees here, we're going to actually reduce this down to make it a little bit more realistic, 20 degrees. So now we can see we've got a really nice smooth shape to that, and that's going to make it easier for the system to track. The other aspect that we do need to mention before we move on is the fact that for our demonstration here, we've made really simple block changes. So we haven't varied our cam timing there in respect to our manifold pressure at all. We've just run the same timing irrespective. With a turbocharged engine, it's worth understanding whereabouts we are moving through this table. So we start somewhere like here, and we're going to be tracking up to about 250 kPa, and then as the RPM increases, we're actually tracking back down. So what I'm getting at here is that 5,000 RPM, we may find that the ideal cam timing is in fact 42, 34 degrees, but we may find that down in the lower load areas that the cam timing wants to be something significantly different. Now, of course, in general, we're actually going to be building up our steady state timing targets first, and we'll already have addressed this lower region of the table. But it's important just to explain that we're just making these block changes for simplicity for this demonstration, and we certainly wouldn't want to leave our table with these large steps that we're seeing here. So this is not representative of a real world table. It's just for the purposes of our demonstration. The other aspect with the block changes we've made is that we can see we've got this big ugly step here down at low load. Now, of course, that's not representative of what we'd want there. Stepping between, particularly here, 0 and 45, 48 degrees across a relatively shallow change in manifold pressure, that's going to really make our cam timing job, or the cam control job, very difficult to achieve those targets. But this again isn't realistic of what we'd actually end up with, and is just for the purposes of this demonstration.